Hello, good afternoon, everyone. Um, in stage 10, we will have a recapitulation of light ray and waves because that is the ending chapter of the stage 9. So, what we learned in the first slide is that here is the incident ray and here is the reflected ray, and this angle of incidence is equal to angle of reflection. This is the first property of the light, which is nothing but the reflection property of the light. And in order to determine the position of the image, here is a simple experiment wherein you place a scale in such a way that you view the image and draw a straight line from one end or one point. Similarly, from any other point, you can have another scale and draw another line so that these two lines intersect at each other. This point of intersection of two extended rays is called as image, but this image is the virtual image. This already we have done in our classes. This is how we can find out or locate the position of the image with respect to the object. Here is an example how cat is trying to view its image in the mirror, plane mirror. And here is another example where the bulb is acting as an object and its image is found in the reflection, wherein there are two incident rays incidenting on the mirror and reflecting. These two extended reflected rays meet at one point. This point of extension of reflected rays gives us the image of the object. Here is an example how the image gives not only upside down inversion but also lateral inversion. The spelling of ambulance is lateral inverted here, and this is what we find out the image on the right, where the spelling is up, properly visible. Here is a simple numerical example wherein the angle is given with respect to ground as 55 for the plane mirror. And as we know, the angle A must be 55 because it's an alternative angle. Then if addition of A and B gives us the 90 degrees angle with respect to normal, then we will get the B value from this, because 90 minus 55 will get the angle of B, that is angle of incidence. Then if you know the angle of incidence, we can also find out angle of reflection, that is angle C. All this we have discussed already in our previous classes. This is another example. This is another example, similar example. Here also we have 90 degrees for angle B and C. Then angle of incidence must be here 45 obviously. Then C is also 45. So in this way we can also solve this problem. All this we have discussed in our previous classes. I'm just trying to recapitulate. This is an example of refraction. This is another property of the light ray, where when you place an object in the another medium with respect to first medium, the light ray refracts, and apparently the objects appear to be bending because the light is actually bending. Here we find that there is a glass slab, and here is an incident ray, and next stage is the refracted ray. Because when light ray is traveling from A to or rarer medium to denser medium, it moves towards the normal, and when it is moving from denser medium to rarer medium, again it moves away from the normal. So this is how refraction takes place with respect to glass slab. And this is the extension of the incident ray, which is parallel to the emergent ray, which is coming out of the glass slab. This property of refraction we find out even in water surfaces, in the water medium as well. That is not only in terms of light, in terms of water waves also. So this is how the water waves bend when it is moving to other medium. And here in this case, it is given as the light ray refraction. This is the wavefront of all the different light rays. And what we learned so far is that what happens when light ray is entering? It bends towards normal, and the reason is because speed is changing, because the medium is changing and density is changing. Is there any possibility for no refraction? Yes. When is it possible? Only when angle of incidence is 0. That means when light ray is passing through normal. Only in this condition we find out no refraction. We can also say that Here angle of incidence is equal to 0. That means angle of refraction must be 0. Refraction must be 0. Here is another example where is the object is given as a goldfish within the water and its image is apparently raised up. This is because of the property of refraction. So if the incident rays are passing towards the eye at the plane separating two mediums, there is a refracted ray, and if you extend this refracted ray behind, this gives us the point of intersection of two refracted rays, and here there is the image we find, and the distance between object and the surface level is real depth, and image and surface level is apparent depth. From this we can know what is the refractive index, because there are two mediums. We speak about the refractive index of the given medium with respect to another medium. So therefore refractive index symbol N is equal to C by V, where speed is the speed of light in vacuum and V is the speed of light in given medium. It can be water or glass, anything else. So formula of refractive index N is equal to C by V. It can also be called as mu, not only N. Refractive index can be represented by mu as well. Mu is equal to C by V. This refraction we also find out not only in glass labs, not only in water, we can also find out in prism. So here also we find out the phenomena of refraction occurring. So here when light ray is incidenting on the prism, it refracts as it passes through glass slab. Here in this case prism. So it not only refracts but it also splits light into 7 colors, because the input given here is white color and we get the output as 7 colors. So here two phenomena you are observing. One is refraction as well as dispersion of light. Then this property of refraction we can also extend further, that is total internal reflection. Here the light ray is trying to pass from denser medium to rarer medium. Denser medium here is below the line, horizontal line here in middle. So here denser medium is glass and rarer medium is air. And when the light ray is reflecting inside backwards, the angle of incidence is equal to angle of reflection. How can this be possible? Let us see that. Here if you notice in the first diagram, the incident ray is less. So when light ray is traveling from glass to air, it is refracting away from normal. But in the second image, we can find out that the angle of incidence is increased further, wherein angle of refraction is 90 degrees. So during that position, we can see that the angle of incidence is equal to critical angle. So this is the angle of incidence, wherein angle of refraction is 90 degrees. This positioning of this angle we call it as critical angle. Then in image 3, we can see that the angle of incidence is increased further, greater than critical angle. So here angle of incidence is greater than critical angle. Therefore, instead of only having refraction, the refraction is extended little further, and what happens is there is no possibility for further refracting. So it refracts beyond and light ray comes back into the same medium, again back to the denser medium. So this is how total internal reflection takes place. So during this positioning, we find out angle of incidence is equal to angle of reflection. These are some of the values of refractive indexes of different mediums and their critical angles accordingly. So this is the overview of the entire phenomena of TIR. TIR with respect to prism, here incident ray in the first image is going straight without any deviation, without any refraction, because here angle of incidence is 0. That means incident ray is passing through the normal. Then at other surface, the angle of incidence is such that it makes angle 45, which is greater than 42, which is the critical angle of the prism. So therefore, instead of refracting, it comes back into the same medium, that is prism. Then at the third surface, again there is no refraction because here angle of incidence is 0. The same phenomena occurs in the second picture as well. So in this way we can find how total internal reflection also takes place in the prism, not only in the water. So here is an example of periscope. Previously, mirrors were used, but now we are using prism also because prism gives much more clear image compared to the mirror. These are the examples of applications based on total internal reflection, wherein diamond shines, glitters because of the phenomena of total reflection, because the critical angle of diamond is less, that is 24, and therefore any light ray which is having angle of incidence greater than critical angle easily able to refract, and the light ray is reflecting internally because of the TIR. Here also in the desert we can also find out mirage is also caused due to the TIR phenomena, wherein the ground surface is having hot air and the upper layers are having cold air. So when light ray is passing from denser medium, that means cold air in this case, it moves away from the normal, and in this way TIR takes place. So from different layers, the TIR goes on in such a way that it reflects back into the same medium. And if you extend the ray, that ray gives the image of the object. So that is apparently appearing as a image. This is the same concept with a different image. This is application of the TIR in submarines and all. So here we can find out the maximum technology used using optical fibers, the concept of TIR, because we know that light ray is having the maximum speed with respect to any other way that is possible. So light ray moves fastest than any other material or the medium that is possible existing. And because of this property, there are many applications. Here are some of the uses that the fiber optical cables are functioning with: internet cables, communication, computer networking, medical, military, and lighting, and even in mechanical inspections. All this we have discussed already, but just trying to recapitulate. Here is about Snell's law. Here is a derivation of the Snell's law, wherein we use refractive index value and formula n is equal to c by v. And what is Snell's law? Snell's law states that ratio of sine of angle of incidence to the sine of refraction is constant. So n is equal to sine A by sine R. So taking two mediums here, that is one medium is air, other medium is water. So n1 is equal to c by v1. Similarly, n2 is equal to c by v2 because n is equal to c by v. Then taking v1 and v2 as subjects, we get c by n1 and c by n2. Then taking the ratio of the two speeds of light, that is v1 by v2 is equal to c by n1 by c by n2, that is equal to n2 by n1. Then that is also equal to sin A by sin R, because we are getting v1 by v2 is equal to sin A by sin R, because we are comparing the speeds with respect to the sine angle. Therefore, by solving, what we get is n2 by n1 is equal to sin theta 1 by sin theta 2, because angle of incidence is equal to theta 1, angle of refraction is equal to theta 2. And the final equation is n1 sin theta 1 is equal to n2 sin theta 2. Here is a numerical example of the equation that is being used. Here refractive index of glass is 1.5, but we know that speed of light is in air is 3 into 10 power 8 meters per second. Then taking subject of speed of light in a glass, because here glass is a medium, we will get the value as 2 into 10 power 8 meters per second. Here is one more numerical example, wherein we are trying to find out the angle of refraction based on the formula n1 sin theta 1 is equal to n2 sin theta 2. From here, what we finally derive is theta 2 value, because that's what is being asked, angle of refraction based on this equation. Same derivation in different way. Okay, so by here we'll complete our class for today. And with respect to so far the slides that we have used, I'll forward a worksheet and a video as well, so that you can have some reference to it. And next concept we'll start with lenses. I'll just recapitulate even lenses and forward another PPT as well. Thank you for today.